Hey, so this is going to be the last section of probability, and we're going to talk about conditional probability and independence today. So you can see these are the 5 topics that we're going to cover. So we're going to discuss what are conditional probabilities, how can we use the general multiplication rule to calculate probability, how can we use tree diagrams to model probability rather than just to model outcomes. How do we determine if 2 events are independent of each other? And when is it appropriate to use the multiplication rule of independent events? And so this is going to be part 2. These 2 are part 2, and this is part 1. So let's go ahead and look at the example we looked at yesterday. And we're talking about this guy's getting his ears pierced, so we're comparing event A is the males and event B is pierced ears. So the probability of being male is here, so it's 90 out of the total, which is 178. The probability of pierced ears is here, 103 out of 178. And here we're looking at the probability of the intersection, or we call this AND. So it's like if you had a Venn diagram, it's the part that's both that we're interested in, and that would be here, 19 out of 178. And here's the union. So the union is, you'll see the word or sometimes, and that means it's the combination of both sets. And you have to be careful not to count that middle part twice, because it does kind of show up in both. And so what we look at is we look at all the stuff that's pierced and male, but you're not including that section right there. So it's 174 out of 178. So that's what we talked about yesterday. Today we're going to kind of make it a little bit more, we're going to talk about like conditional probability. And the key word is going to be given, right? So we want to know that if a randomly selected student has pierced ears, so that's our given, what's the probability that the student is male? So we're going to say the probability that a student is male is event A, given event B, that the student has pierced ears. And so when you look at this, we're going to look at the probability that a student is male with pierced ears is 19, and that's going to be out of the total number of students with pierced ears. Sorry about that distraction. I tried to get it before. All right, so maybe that'll be the last bell ring. We'll see. All right, now here we're going to look, and we're going to say the probability of pierced ears, which is P, given the student is male. And so in this case, again, it's 19, because that's both of them together, the intersection of them. And then, but this time it's going to be over 90, because 90 is the amount of students that are male. Right? And if you divide that out, you get a decimal, and all will be good. All right, so this is what we call conditional probability. Conditional probability is the event that 1 happens, given, and the symbol we're going to use to represent given is a line, given another event has already been known to happen. So how would we say this? We would say this is the probability of event A given B occurred. So let's look at another example. In this case, we're looking at, we want to know B given A. So the event is pierced ears given the student is female. So the union of the two, not the union, the intersection of the two is 84. That's females with pierced ears. And the total number of females is 88. So the probability of B given A would be 84 out of 88. Okay, another example, if we're looking at schools, it's been known that if you're an engineering or physical science student, your grades tend to be lower than if you're an ELA student. So let's look at some comparisons. So the first thing, we're going to define event E as a grade comes from an EPS course, or engineering and physical science, and we're going to call L the grade is lower than a B. So the first thing we want to do is find the probability of L. And so if we look, we got to count up all the L. So if we add these 3 numbers together, you get 3,656. So the probability of L is 3,056, and I added up all the grades all the students in the school, and there were 10,000. So the probability of getting below a B is 3,656 out of 10,000. Now let's look at some conditional probabilities. We want to find the probability of E given L. So we want to know how many students are both in engineering and have grades lower than a B. And that would be this overlap right here.
Gustavo Diego,
so it's 800, and then we want to know given L. So L is 3,656. Okay, in this case, again, we need the intersection of L and E, which is 800, but this time we're given E, which is the amount of engineering and physical science students. And that is actually, dang, there's a lot of bells at this time, 1,600. So this is going to be 800 over 1,600. And then if you actually divide those out, you get your probabilities. The pattern we should be noticing is that if you are finding a conditional probability, you should notice that what goes on top is the intersection of the two. So that's the part here. This is what we call the intersection, right? The intersection of the two is here. It kind of looks like a face. And then the one on the bottom is the other event that's given. So in this case, it was L, and in this case, it was the total number of students in the engineering department. And we can look, and that is, of course, our formula. It is the intersection over the given information. And so in this situation, we've got an apartment complex where there are 40% of the residents read USA Today, 25% read the New York Times, and 5% actually read both. Okay? So there's going to be 100 residents. So we're going to go ahead and draw our Venn diagram. And we know that 40, this we'll call USA Today, event A, and we'll call the New York Times, event B. So 25 out of 100 read the New York Times, and then we know that 5 are on the inside here. Now the rest of the people that don't read either paper, we don't really care about them. So we want the probability of B given A. So the first thing we need is the probability of A intersecting B, and we're going to put that over the probability of A. So the intersection is 5, and the probability of A is 40, and so this would be our probability for the conditional probability of both. So that's the formula. Let's look at another example. Maybe not. The next example is if you're playing sports. So we want to know the probability. Now this time we're going to look at the probability rule for any two events. So if we want to know two events combined, not given one and the other, we want to know the probability of A and B. This is where we want to find the intersection of the two when we don't have a Venn diagram or we're not given that information. How can we figure that out? And so what we can do is we can first look at the probability of event A. In this case, it is 55% of high school students participate on the team. And then we want to know the probability of B given A. In this case, it is 5% of these athletes go on. So given that they're high school students, 5% of them go on to play college. And so we want to know what percent go on to play in the NCAA. And so what we would do is we would take the probability of A, which is 0.55, times the probability of B given A, which is 0.05, multiply those together, and you end up with 0.0275. So about 30% of the students actually go on to play if they participate in a high school team. Let's look at another example. So this is going to kind of combine everything we've talked about so far. Find the probability that a student chose to fly as their superpower. So here we've got fly right here. So it's 38 out of 100, or 0.38, thank goodness. Find the probability that a student was male. So we're going to look here at our total, which is 48 out of 100, which is 0.48. Find the probability the student was male given they chose to fly. So we need the intersection of the two. So where is male and flying? It's right here. 26 out of the amount that like to fly, which is 38. And now we're going to look at the opposite, which is the probability that they fly and they're male. So this would be 26 out of 48. Okay? And this equals 0.68. And this equals 0.51. And so the question is, can you reverse the order? No, it is important that you put the given information last, because if you change the given information, you do get different percentages. So order, you cannot reverse the order and get the same probability either way. So this is no, order is important. A couple more examples, and I'll send you on your way. So here's how we can use a tree diagram. Actually, I'm going to put this as part 2.